So here we are given that x is cosine of theta plus I times sine theta, and y is given by cosine of phi plus I times sine of phi. Then we need to prove the following. So let's begin with number 1. So in part 1, first we'll start with x equals to cosine of theta plus iota times sine theta. Now we're going to raise both sides with the power m. So we have x raised to the power of m, that will be given by cosine of theta plus iota times sine theta whole raised to the power of m. So here we can use the De Moivre's theorem and we can rewrite it as cosine of m theta plus iota times sine of n theta. So now what we'll do, we'll consider x and now we will raise it both sides to the power of negative m, such that we have cosine of theta plus iota times sine of theta whole raised to the power of negative m. So this means we will have cosine of negative m theta plus iota times sine of negative m theta. Now we know that cosine is an even function, so cosine of negative m theta will be simply equals to cosine of m theta. And sine being an odd function, the sine of negative m theta will make it negative sine m theta, which gives us negative iota times sine of m theta. So let's label this first one as equation number 1 and the second as equation number 2. Now we'll start with number 1, since we have to find out x raised to the power of m plus x raised to the power of negative m. We will add 1 and 2. Then this is going to give us 2 times cosine of m theta. So here iota times sine m theta. So this will get cancelled out. Right. And to prove part 2, what we'll do, we will take x raised to the power of n and from it we're going to subtract x raised to the power of negative m, such that we get 2 iota times sine of m theta. Right. So we have successfully shown number 1 and number 2. Now we will go to 3 and 4. Let's do that. So first we will consider x equals to cosine of theta plus iota times sine of theta. So when we raise x to the power of m, then we will have cosine of m theta plus iota times sine of m theta. And if we raise x, so again using 1, if we raise x to the power of negative m, then we will have cosine of m theta minus iota times sine m theta. So we already covered this in the previous problem in part 1 and 2. Then we will also find out, we'll have y given by cosine of phi plus iota times sine phi. Now when we raise y to the power of n, then we have cosine of n phi plus iota times sine of n phi. And y raised to the power of negative n, so this is going to give us cosine of n phi minus iota times sine of n phi. So let's label all of them. So we're going to label this as number 1, this is going to be 2, this let it be 3, and this be 4. Now we'll start from number 3. So we'll start from the left hand side. So we have x raised to the power of m times y raised to the power of n plus x raised to the power of negative m multiplied to y raised to the power of negative n. So this is going to give us, so we'll use all the equation 1, 2, 3 and 4. So x raised to the power of m, that's cosine of m theta plus iota times sine of m theta. So this will get multiplied to y raised to the power of n. So this is cosine of n phi plus iota times sine of n phi. Now this is multiplied and this will now get added to y raised to the power of x raised to the power of negative m, which is cosine of m theta minus iota times sine of m theta. This will be now multiplied to y raised to the power of negative n. So here we have cosine of n phi minus iota times sine of n phi. Right. So let's further simplify this. So we're going to multiply cosine of m theta plus I sine m theta with cosine of n phi plus I sine n phi. So this is going to give us Next we multiply cosine of m theta minus iota times sine of m theta with cosine of n phi minus iota times sine of n phi, which should give us now iota square. We know iota square, this value is -1, and we have here iota square as well, so this will become -1. So we have cosine of m theta, cosine of n phi minus sine m theta, sine n phi. So this is actually cosine of m theta minus n positive n phi added to iota times sine. So this entire expression is the expansion of sine m theta plus n phi added to. So here we have cosine of m theta times cosine of n phi negative sine m theta. So this is the expansion of cosine of m theta plus n phi plus iota times negative iota times sine of m theta plus n phi. So here the second term and the fourth term cancels out, so we're left with the first term and the third term, which is 2 times cosine of m theta plus n phi. So we have successfully proved part 3 as well. So here in part 3 we have shown that it is 2 cosine of m theta plus n phi. So this is done. Now let's go to number 4. We will use the results obtained in part 3. So let's begin from the left hand side of part 4. So we have x raised to the power of m. So x raised to the power of m is cosine of m theta plus iota times sine of m theta. So this gets multiplied, whole gets multiplied to y raised to the power of -n, which is equation number 4. So this will be cosine of n times phi minus iota times sine of n times phi. Fine. This is now added to x raised to the power of -m, so which is equation number 2, cosine of m theta minus iota times sine of m theta. So this will get multiplied to y raised to the power of it. So we'll use equation number 3. So this will be cosine of n phi added to iota times sine of n phi. Fine. So let's perform the multiplication. So we will get, so now this entire expression is equivalent to cosine of m theta minus n phi plus iota times, so this expression is the expansion of sine m theta minus n phi plus, so this expression will be cosine of m theta minus n phi minus iota times sine of this particular expression, which is simply m theta minus n phi. So here we have the second term and the fourth term cancelling out. So the first term and the third term, they are same. They get added to give us 2 times cosine of m theta minus n phi. So here also we have successfully shown that the expression is equals to 2 times cosine of m theta minus n phi.